August 9, 1944, 2:37 hours. Rail yard outside Aulnoy-Emery, France. Oberfeldwebel Heinrich Müller, 31 years old, stands on a steel platform that shouldn't exist, operating a weapon in a place it was never designed to be. Beneath his feet, a modified Deutsche Reichsbahn railway flatcar trembles on the tracks. Above him, a 10.5-centimeter Flak 38 naval anti-aircraft gun, ripped from a Kriegsmarine destroyer that never left port, traverses on powered mounts that draw electricity from cables running the length of the train. The mathematics seem impossible. The gun weighs 26,000 pounds. The mount adds another 8,000 pounds. The ammunition, 40 rounds of 105mm shells in armored magazines, adds 4,200 pounds more. All of this sits on a railway car designed to haul freight, not absorb the recoil of a naval weapon firing at 15 rounds per minute. Müller's commanding officer, a Luftwaffe major who looks like he hasn't slept in a week, had briefed the crew yesterday with the kind of exhausted pragmatism that comes from losing a war. The Allies own the sky. Their heavy bombers come in formations of 500 aircraft. Our fighters are grounded for lack of fuel. Our static flak positions get bombed into rubble before they can engage. We need mobile anti-aircraft capability that can redeploy faster than Allied reconnaissance can locate it. This railway flak is our answer. In 18 minutes, RAF Bomber Command's Pathfinder aircraft will cross the French coast, heading for industrial targets in the Ruhr Valley. Müller's railway gun, designated Flak Trig 437, will attempt something no pre-war doctrine ever imagined, providing mobile anti-aircraft defense from a moving train. He has no idea if the mounting can withstand sustained firing, no idea if the railway car's brakes can handle emergency stops while the gun fires. No idea if this desperate improvisation can actually hit aircraft traveling 250 miles per hour at 20,000 feet altitude. But in 18 minutes, he'll discover whether German engineering ingenuity can offset Allied material superiority, or if this railway gun is just another futile gesture in a war already lost. The Second World War had created a problem that pre-war military planners never anticipated: the complete obsolescence of static air defense in the face of strategic bombing campaigns operating at scales that seemed impossible in 1939. By mid-1944, the Allied combined bomber offensive had achieved air superiority over Western Europe. American 8th Air Force and RAF Bomber Command flew thousands of sorties monthly, targeting German industrial capacity, transportation networks, and urban centers with progressively devastating effect. German air defense networks, the Luftwaffe's fighter force, and the extensive Flak artillery system faced insurmountable vulnerabilities. Allied fighters, P-51 Mustangs, P-47 Thunderbolts, Spitfires, escorted bomber formations with sufficient range to reach any target in German-controlled territory. German fighters increasingly lacked fuel, spare parts, and experienced pilots to mount effective interception. This left Flak artillery as Germany's primary air defense capability. The Luftwaffe operated approximately 15,000 anti-aircraft guns of various calibers by 1944, from light 20mm weapons to massive 128mm guns that could engage bombers at extreme altitudes. But static flak positions suffered critical vulnerabilities. Once located by Allied reconnaissance, a process taking hours or at most days, they became targets for subsequent raids. Heavy bombers would saturate flak positions with high explosives before main formations arrived, suppressing defensive fire. Intelligence reports from RAF Bomber Command documented the pattern. During raids on the Ruhr Valley industrial region in early 1944, German flak shot down approximately 3.2% of attacking aircraft. By July 1944, that figure had dropped to 1.8%, not because German gunnery deteriorated, but because Allied tactics evolved to neutralize static positions before they could engage effectively. The Luftwaffe's Flak command recognized the problem by late 1943. Static positions provided predictable targets. Mobile flak units, guns mounted on trucks or half-tracks, offered better survivability but lacked the heavy calibers needed to engage bombers at operational altitudes above 20,000 feet. Mounting heavy flak guns on vehicles presented engineering challenges that seemed insurmountable. The 8.8-centimeter Flak 3637, Germany's standard heavy anti-aircraft gun, weighed 16,000 pounds with its cruciform platform deployed. The recoil forces generated when firing required a stable platform anchored to the ground. Attempts to mount 88mm guns on tank chassis had produced the famous Flak 88 self-propelled variants, but these were primarily designed for anti-tank roles and couldn't elevate sufficiently for effective anti-aircraft fire. Heavier guns faced worse problems. The 10.5-centimeter Flak 38 and 12.8-centimeter Flak 40, capable of engaging aircraft at altitudes up to 35,000 feet, weighed 26,000 and 60,000 pounds respectively. No practical vehicle could carry such weapons while providing stable firing platforms. But Germany's extensive railway network offered a different possibility. Railways could transport heavy loads that would immobilize road vehicles. Railway cars provided stable platforms when stationary. And critically, trains could redeploy faster than Allied reconnaissance to strike cycles, potentially allowing heavy flak guns to survive by constantly relocating. The concept of railway-mounted artillery wasn't new. Germany had employed railway guns extensively during World War I, with weapons like the Paris gun shelling targets from ranges exceeding 75 miles. During World War II, massive railway guns like the 80-centimeter Schwerer Gustav had bombarded fortifications with shells weighing 7 tons. But those were railway guns designed from inception for rail mounting, with specialized cars built to handle their enormous weights and recoil forces. What the Luftwaffe needed in 1944 was different, adapting existing anti-aircraft guns to railway carriages quickly and economically using available materials and manufacturing capacity. The program began in late 1943, driven by a Luftwaffe Technical Office directive that authorized experimental railway flak mountings using standard Reichsbahn freight cars. The initial concept specified several requirements. Weapons must be existing flak gun models, not new designs requiring development time. Mountings must use standard railway cars with minimal modification to preserve rail transport capacity for other military needs. Installations must allow firing while the train was stationary without requiring stabilizing outriggers or ground anchors that would slow deployment. Crews must be able to operate guns using standard flak doctrine and training, minimizing retraining requirements. The Reichsbahn Technical Bureau, responsible for German railway operations, partnered with Krupp and Rheinmetall, Germany's primary artillery manufacturers, to develop prototype systems through winter 1943-44. The first successful mounting emerged in February 1944, a 10.5-centimeter Flak 38 naval variant mounted on a reinforced Reichsbahn Type SSY flatcar. The weapon choice was deliberate. Naval flat guns used pedestal mounts designed for installation on ship decks, making them more adaptable to railway platforms than Army guns designed for ground emplantments. The 10.5-centimeter Flak 38 fired a 33-pound high-explosive shell to altitudes exceeding 31,000 feet at a cyclic rate of 15 rounds per minute. Its naval mounting included powered traverse and elevation mechanisms, electrical fire control integration, and a compact footprint that ship designers have optimized for destroyer and cruiser installations. Adapting the naval mount to a railway car required solving several critical engineering challenges. The first involved recoil management. The 10.5-centimeter Flak 38 generated approximately 45 tons of recoil force when firing, directed rearward and slightly downward depending on elevation angle. Naval installations absorbed this force through the ship's mass and structural strength. A railway flatcar lacked comparable mass and couldn't be anchored to the ground during firing without defeating the purpose of rapid mobility. Krupp engineers designed a recoil compensation system using the railway car itself as a mass anchor. The gun mount bolted to a steel platform that spanned the entire flatcar and extended brackets that gripped the car's frame rails. When the gun fired, recoil forces distributed across the car's entire structure rather than concentrating at the mount point. Additionally, the railway car's suspension, leaf springs, and friction dampers designed to smooth ride quality provided some recoil absorption. Engineers stiffened the suspension with additional springs and hydraulic dampers borrowed from heavy truck designs, creating a system that could handle firing loads without permanent deformation. Testing at the Krupp Proving Grounds in March 1944 demonstrated the concept's viability. The railway-mounted 10.5-centimeter Flak could fire full-rate salvos of 15 rounds per minute without structural failure of the mounting or railway car. Accuracy proved acceptable, though not matching the precision of purpose-built ground emplacements. The second challenge involved electrical power. The Flak 38's powered traverse and elevation required 220-volt three-phase AC power, typically supplied by shipboard electrical systems or dedicated generators at static positions. Railway mounting solutions used a diesel generator car coupled directly behind the gun platform. A 150-kilowatt generator, originally designed for powering railway workshop equipment, provided sufficient electrical capacity for gun operation, plus lighting, fire control equipment, and crew facilities. Power cables ran along the coupled car's frames, connecting through heavy-duty connectors that allowed the train to move while maintaining electrical continuity. The system worked, but introduced vulnerabilities. Damaged cables could disable the gun even if the weapon itself remained functional. Fire control presented the third major challenge. Effective anti-aircraft gunnery required predicting where an aircraft would be when shells arrived, accounting for aircraft speed, altitude, heading, and the shell's ballistic trajectory. Static flak positions used elaborate fire control systems, optical rangefinders, mechanical computers that calculated firing solutions, and electrical transmission systems that automatically positioned guns to intercept targets. These systems weighed thousands of pounds and required stable platforms. Railway flak installations used simplified fire control. A Flak 40 fire control director, a compact optical rangefinder combined with a mechanical ballistic computer mounted on the gun platform. The director could calculate basic firing solutions for targets up to 30,000 feet altitude, though with less precision than larger static systems. Crews were expected to employ area barrage fire rather than precision engagement, filling volumes of airspace with exploding shells that bomber formations would fly through, relying on probability rather than accuracy to achieve hits. Ammunition storage and handling required careful consideration. The 10.5-centimeter Flak 38 fired separate loading ammunition, a 33-pound projectile, and a brass cartridge case containing the propellant charge. Static positions stored hundreds of rounds in protected magazines. Railway installations had limited space and needed to balance ammunition capacity against weight restrictions. The final design included 2 armored ammunition cars coupled on either side of the gun platform. Each car carried 40 rounds of ready ammunition, projectiles in one section, propellant charges in another, plus fire control equipment, crew quarters, and supplies. Total ammunition load of 80 rounds provided approximately 5 minutes of sustained firing before requiring resupply. The complete Flakzug, Flak train, consisted of 5 cars, diesel generator car, ammunition/crew car, gun platform car, ammunition/crew car, and a command car housing communications equipment and the train commander's station. Total length, approximately 230 feet. Total weight, 287 tons loaded. The Reichsbahn could move such trains at speeds up to 45 miles per hour on main lines, slower on secondary tracks. Deployment time from travel configuration to combat ready, approximately 8 minutes, including stopping the train, extending stabilizing jacks, and bringing fire control systems online. Production authorization came in April 1944. Initial orders specified 12 Flakzug units, later expanded to 27 as the concept proved operationally viable. Manufacturing utilized weapons and equipment from various sources. Some 10.5-centimeter Flak 38 came from incomplete naval vessels. By mid-1944, Germany's naval construction program had effectively ceased. Allied air attacks prevented completion of destroyers and cruisers on the building ways. These incomplete ships provided sources of naval weapons that could be repurposed for land defense. Other guns came from coastal defense positions. The Atlantic Wall fortifications, built to repel Allied invasion, included numerous naval-caliber Flak positions defending ports and naval facilities. After D-Day demonstrated that static coastal defenses couldn't prevent Allied landings, some positions were stripped of weapons for redeployment. Railway cars came from Reichsbahn stocks, modified at railway workshops in Essen, Munich, and Berlin. The modifications were substantial: reinforced frames, modified suspension, mounting platforms, but could be completed in approximately 3 weeks per car using skilled railway maintenance personnel. By July 1944, 11 Flakzug units were operational, deployed across Germany and occupied France. Crews consisted of Luftwaffe Flak artillery personnel, typically 8 men per gun. Commander, 2 layers, 1 for traverse, 1 for elevation, 2 loaders, 2 ammunition handlers, and a fire control operator. If you want to see how these railway Flak batteries performed in actual combat, defending against 1,000 bomber raids while constantly relocating to avoid Allied countermeasures, hit that subscribe button and notification bell. This story gets even more intense, and you won't want to miss the moment when Oberfeldwebel Müller's crew engaged RAF Lancaster bombers in the darkness over France. Back to Flakzug 437 and that August night in 1944. The 10.5-centimeter Flak 38 mounted on Müller's railway car was serial number M4478, originally manufactured in November 1942 for installation on the destroyer Z-43. That ship was never completed. Repeated Allied bombing of the Deutsche Werke shipyard in Kiel delayed construction until the Navy canceled the project in March 1944. Understanding the weapon system requires examining each component and how railway mounting modified naval equipment for ground-based air defense. The 10.5-centimeter Flak 38 was a refined version of earlier German 105mm anti-aircraft guns, incorporating lessons learned from years of combat. The designation 10.5 centimeter referred to the bore diameter, 105 millimeters or 4.13 inches. The barrel measured 60 calibers long, 6.3 meters total length, providing the velocity needed to engage high-altitude targets. The weapon itself fired a 15.1 kilogram, 33.3-pound high-explosive shell at a muzzle velocity of 880 meters per second, or 2,887 feet per second. This combination delivered sufficient energy to reach altitudes of 9,450 meters or 31,000 feet with adequate lethality to damage or destroy heavy bombers. The shell itself measured 105 millimeters in diameter and 420 millimeters in length, with a streamlined ogive shape that minimized drag. The projectile body was mild steel, machined to precise tolerances, filled with 1.6 kilograms of TNT-based explosive. A time fuse in the nose, set before firing, detonated the shell at a predetermined altitude, creating a fragmentation pattern designed to damage aircraft within a 30-meter radius. The naval mount provided powered traverse and elevation through electric motors. Traverse covered a full 360 degrees at speeds up to 12 degrees per second. Elevation ranged from -3 degrees, slightly below horizontal, to +80 degrees, nearly vertical, at 8 degrees per second. These speeds allowed the gun to track fast-moving aircraft, though not with the precision of smaller caliber weapons. For railway mounting, engineers modified the naval pedestal to bolt onto a reinforced steel platform rather than a ship's deck. The modification added approximately 800 kilograms, 1,760 pounds, through additional bracing and a wider base that distributed loads across the railway car's frame. The platform itself was a masterwork of structural engineering. Fabricated from 25mm steel plate, it formed a cruciform shape that spanned the flatcar's width and extended fore and aft to anchor points on the car's frame rails. 4 large bolts, each 50 millimeters in diameter, secured the platform to the car through reinforced mounting brackets welded to the frame. The railway car's suspension required substantial modification. Standard Reichsbahn Type SSY flatcars used leaf spring suspension designed for loads up to 50 tons, distributed relatively evenly across the car's length. The Flak mounting concentrated 34 tons at a specific point, creating stresses the original suspension couldn't handle. Reinforcement used additional leaf springs stacked in compound arrangements, supplemented by hydraulic dampers positioned at each wheel truck. The dampers, borrowed from heavy mining equipment, absorbed shock loads during firing and prevented oscillations that would degrade accuracy. Even with reinforcement, the car's structure experienced significant stress during firing. Metallurgical analysis after the war found stress fractures in the frame rails of several captured railway flak cars, indicating the mounting pushed structural limits even with engineering modifications. The recoil system used a combination of mechanisms. The gun itself incorporated a hydro-pneumatic recoil buffer that absorbed initial recoil energy, limiting the impulse transmitted to the mounting. This buffer consisted of a cylinder filled with hydraulic fluid and compressed nitrogen gas that acted as a shock absorber during firing. The gun would recoil approximately 800 millimeters, 31 inches, rearward during firing, compressing the buffer, then return to battery position as the compressed gas forced it forward again. This cycle took approximately 0.4 seconds, limiting firing rate to 15 rounds per minute maximum. Secondary recoil absorption came from the railway car's suspension and the mass of the car itself. When the gun fired, the car would rock backward slightly on its suspension, then settle as the springs and dampers dissipated energy. Crews learned to brace for this motion, timing their movements to the gun's firing cycle. Fire control equipment mounted in an armored housing on the gun platform's forward section. The primary component was a 4-meter optical rangefinder, a long tubular device with precision lenses at each end that measured distance to targets through stereoscopic triangulation. The operator would view the target through both eyepieces, adjusting controls until the two images aligned. The rangefinder would then display target distance with accuracy of approximately plus or minus 200 meters at ranges up to 12,000 meters. This distance fed into the fire control computer, a mechanical calculating device that resembled an elaborate adding machine. The computer accepted inputs for target range, altitude, speed, and heading, plus meteorological data like wind speed and air temperature. It then calculated the required gun elevation and traverse angles to place shells in the target's future position. The computer used a system of gears, cams, and mechanical linkages to perform these calculations, achieving solutions in approximately 15 seconds. Electrical outputs from the computer drove indicator dials that the gun layers would match by adjusting traverse and elevation, or in automatic mode, the computer could directly control the gun's positioning motors. Accuracy of this system was limited compared to larger static fire control installations. The railway mounting's smaller rangefinder and simplified computer introduced errors that reduced hit probability. Operational doctrine compensated through volume of fire, multiple guns firing in coordinated patterns to saturate airspace rather than achieving precision hits. Ammunition handling on the railway flak required careful choreography. The 105mm Flak 38 used separate loading ammunition, meaning each round consisted of two components loaded sequentially, the projectile and the propellant cartridge. The projectiles were stored in armored racks in the ammunition cars, nose up in protective foam inserts that prevented damage during transport. Each ammunition car held 40 projectiles in two 20-round racks positioned for easy access from the loading platform. Propellant cartridges, brass cases filled with nitrocellulose powder, were stored separately in environmentally controlled magazines. The cartridges were sensitive to temperature and humidity, requiring storage between 10 and 30 degrees Celsius in low humidity conditions to prevent degradation. Loading procedure required two crew members working in coordination. The loader would retrieve a projectile from the rack, carry it to the gun, a distance of approximately 3 meters, and ram it into the breech using a loading tray. The projectile weighed 15.1 kilograms, awkward but manageable for a trained loader. Once the projectile seated, a second loader would insert the propellant cartridge, a simpler operation, as the cartridge was lighter and aligned easily with the breech. The breech would then close automatically via a spring-loaded mechanism, and the gun was ready to fire. This loading cycle required approximately 15 seconds with a trained crew, limiting practical firing rate to about 12 rounds per minute, even though the gun mechanism could cycle faster. Sustained firing created fatigue that further reduced rates. Handling 30-pound projectiles repeatedly in a confined space, often while the train was rocking from recoil, exhausted crews quickly. The fuse setting mechanism required special attention. Before loading each projectile, a crew member had to set the time fuse to detonate at the correct altitude. This involved using a fuse setter, a wrench-like tool that engaged the fuse's adjustment mechanism and rotated it to a specific position based on the fire control computer's solution. Fuse setting took approximately 5 seconds per round and had to be precise. Setting the fuse for too short a time would cause shells to explode below the target. Too long and they'd explode above or fail to detonate at all. In darkness or under stress, fuse setting errors were common, contributing to the low hit rates railway flak achieved. Electrical power distribution used a 220-volt three-phase system, unusual for military equipment which typically used 110 or 24-volt DC systems. The naval heritage dictated this choice. Warships used 220-volt AC for weapon systems, and adapting the Flak 38 to different voltage would require extensive redesign. The diesel generator car housed a 150-kilowatt three-phase generator driven by a Maybach HL-120 diesel engine, the same engine used in Panzer III and IV tanks. This engine choice reflected Germany's late-war material constraints. Using existing tank engines simplified logistics, even though they weren't optimized for stationary generator operation. The generator ran continuously when the Flakzug was deployed for combat, consuming approximately 12 liters of diesel fuel per hour. Fuel storage in the generator car provided approximately 30 hours of operation before requiring resupply, limiting how long a railway Flak unit could remain deployed without logistics support. Power cables running between cars used armored construction with rubber insulation surrounded by braided steel sheathing. The cables connected through heavy-duty plugs designed for railway applications, theoretically allowing the train to move while maintaining electrical power. In practice, though, these connections were failure points. Rough track could cause cables to disconnect, and battle damage frequently severed power distribution. Communications equipment included radio transceivers for coordination with Luftwaffe air defense networks and telephone lines that could connect to the Reichsbahn's railway telegraph system when parked at stations. This dual-mode communication allowed Flakzug units to receive raid warnings from regional air defense commands and coordinate movement with railway traffic control. The crew quarters in the ammunition cars provided minimal amenities: bunks for 8 men, a small galley with electric hot plate, storage for personal equipment, and a toilet. The quarters were cramped and uncomfortable, with no climate control beyond a small electric heater for winter operations. Operational doctrine for railway Flak emphasized mobility and unpredictability. Unlike static positions that occupied fixed locations, Flakzug units would deploy temporarily along railway lines, engage targets of opportunity, then relocate before Allied forces could target them. A typical deployment cycle lasted 12 to 24 hours. The Flakzug would move to a predetermined location, often a railway siding or junction, deploy for combat operations, engage any Allied aircraft within range, then relocate to a different position before dawn, when Allied reconnaissance aircraft began searching for targets. This constant movement theoretically prevented Allied forces from locating and targeting the railway Flak, though in practice the strategy had limitations. Railway movements were constrained to existing tracks, limiting deployment options. Allied reconnaissance could identify likely deployment locations by studying railway network topology. And the physical signature of a railway Flak position, the distinctive silhouette of a 105mm gun on a flatcar, was difficult to conceal, even with camouflage netting. August 9, 1944, 2:47 hours. Oberfeldwebel Müller stands at his position on the gun platform, watching the eastern sky. The crew has brought the Flak 38 to combat-ready status. Generator running, power flowing to the gun's traverse and elevation motors, ammunition loaded in the ready racks, fuse setters prepared. The railway car sits on a siding outside Aulnoy-Aymeries, approximately 180 kilometers northeast of Paris. The location was chosen carefully, a junction where multiple rail lines converged, providing rapid evacuation routes in any direction. The Flakzug arrived 90 minutes ago, moving slowly through the darkness without lights to avoid attracting attention. Müller's crew consists of 7 men. He's the gun commander, responsible for tactical decisions and fire control coordination. 2 layers operate the traverse and elevation controls, matching indicators to the fire control solution. 2 loaders handle ammunition. 1 fuse setter prepares shells for firing. 1 fire control operator manages the rangefinder and ballistic computer. They've worked together 11 weeks since the Flakzug formed in May. That's longer than most crews survive in the Luftwaffe's Flak service by mid-1944. Losses to Allied bombing have made air defense increasingly hazardous.